Welcome to our introduction to covalent bonding and molecular compounds. Today for our objectives, we want to identify the information a molecular formula provides, and you will be able to explain how electron sharing is involved in creating covalent bonds. The information on this video will be able to help you fill in the front page of the note sheet that you received for homework today. Now, in the past, we've talked about ionic bonds, and we said they form when the atoms will give up or accept electrons, which is followed by an attraction between the cation and the anion that are formed. In a covalent bond, they're held together instead by a sharing of electrons. So one of the major differences here is that ionic bonds involve a transfer of electrons, while covalent bonds involve a sharing of electrons. Think of the atoms as both pulling on those electrons and trying to control them. Sometimes they're going to share evenly, and sometimes they're going to share unevenly. So we classify covalent bonds into two types. There is a polar covalent bond, where they have unequal sharing, and a nonpolar covalent bond, where they have equal sharing. The distinction between them is related to electronegativity. When we take a look at hydrogen and oxygen, hydrogen has an electronegativity value of 2.1. Oxygen has an electronegativity value of about 3.5. The difference between them is therefore about 1.4. That's fairly far apart, but it's not enough of a difference for the oxygen to actually remove the electrons from the hydrogen. The hydrogen still pulls on them as well. However, because the oxygen pulls tighter, the electrons are going to spend more time around the oxygen atom as opposed to being evenly spread throughout the whole molecule. So think about a water molecule for a moment. Oxygen has 6 valence electrons, and each hydrogen is going to have 1. So what's going to happen is oxygen needs 2 more to be stable to reach the octet rule. Hydrogen, having only room for 2, fulfills the duet rule. So they are each going to share a pair of electrons between them. I'm going to represent that with a straight line. Now the arrows I've drawn are representing where the electrons are going to get pulled to more tightly. Oxygen has a greater pull on the electrons. Remember, think right side of the periodic table, smaller radius, stronger pull than the hydrogen do. But they can't actually be removed, so they share them between them. But since the oxygen pulls tighter, it's going to have more control of the electrons. Now something like a nonpolar covalent, it means they share evenly. That would be something like methane. There isn't a very big difference between the electronegativity values of carbon and hydrogen, and everything around the carbon is a hydrogen. So any pulling or attraction of the electrons that's done is even. So in this case, there's no part of the molecule that behaves like it's negative because everything is evenly spread out. All of the electrons are being shared evenly. And it's about the electronegativity. You'll notice in the right-hand column that there's a question about this. Our electronegativity determines the type of bond because the tighter the pull of one versus the other, if there's a greater difference, you will have more likely a polar covalent bond. Remember, from ionic, if the difference is great enough, the electrons actually get transferred. Now, when a covalent bond occurs, the particle that is formed is called a molecule. This is a neutral group of atoms joined together by covalent bonds. So there is no charge on this particular group of atoms. Carbon monoxide is an example. Carbon dioxide is an example. And there are molecules of elements that are formed by two of those atoms bonding together. Di meaning two, atomic meaning atoms. So those initials you see on the right, Hofbrinkel, are the symbols of all of the elements that form these types of molecules. You will have to memorize this. You need to know that these are the elements that form sets of two. You'll notice that they're all nonmetals, and they kind of make an L in the upper right section of the periodic table with the halogens, and then you add in the hydrogen. So all of these are more stable as two of their atoms bonded together than as single atoms. When you have a molecular compound, that's when the atoms in the molecule are of at least two different types. When we talked about ionic compounds, we talked about formula units because those compounds are going to exist in crystalline shapes where you just have alternating patterns of the ions. When I have a molecular compound, the smallest possible unit I can have is a molecule, and then the substance will be made of a whole bunch of those same types of molecules. So when we look at water and you look at these particles here, you have a whole bunch of water molecules in the substance. I can't break it down any smaller than that. But one of the things that can happen is a molecule doesn't necessarily have to be the lowest ratio. So when we looked at something like, say, calcium chloride, we said that's the formula unit because when I cancel out my charges, I will always have one calcium for every two chlorines. But let's say maybe I look at something like glucose, which is a covalent molecule. That is the lowest ratio that forms glucose. I could reduce it. There is a simplest ratio. But in this case, one molecule of glucose has all of those atoms within it. So a molecule is the smallest unit of a molecular compound. The formula unit is typically going to have more than that number of ions, but we report it in the lowest ratio. A molecule does not have to be the simplest ratio that elements can have. Now, there are two particular molecular formulas that are really common that you will have to memorize their common names. We're going to learn a naming system for covalent compounds, but these have really stuck with their original names. So ammonia is NH3, and methane is CH4. Methane is something called an organic compound, and organic compounds have their own special naming system. Because it's such an important organic compound, we name it using that system instead of the regular covalent naming. Hopefully, you'll notice that NH3 ammonia is very similar to NH4 plus ammonium, the polyatomic ion that we've been using in our ionic compounds. That's because ammonia is simply an ammonium without the extra H plus. So ammonia is the NH3, ammonium is the NH4 plus. So, big picture. With these substances, molecules are going to be the lowest substance or particle of a covalent bonded particle. I can have molecular compounds that involved different types of elements. I could also have diatomic molecules where the two are the same type of element. This time it's a sharing of electrons as opposed to a transfer. And that sharing is what allows all of the particles in the molecule to be stable. I can share equally or unequally, and remember that is related to the difference in electronegativity between the elements in the molecule. The greater the difference, the more unequal the sharing of the electrons.